Welcome back, chemistry students. This section is all about elements. You're going to be able to identify the name or symbol of an element given its symbol or name. And you're going to be able to use terms such as atom, element, and molecule correctly. We just got done learning about pure substances and mixtures. And we said that an element and compounds were both pure substances. So remember that elements are pure substances. Each element is abbreviated using a chemical symbol. The symbols are 1 or 2 letters long. Most of the time the symbol is derived from the name of the element. For example, C is the symbol for carbon. Al is the symbol for aluminum. When a symbol has 2 letters, it is very important that the first is capitalized and the second is lowercase. Copper, for example, is capital C, little u. Elements are neutrally charged. So just a copper element, we would look to see how many protons does it have, and that would be equivalent to how many electrons it has. Currently, there are 118 known elements. About 90 are found in nature. The remainder have been created by scientists. This right here is chemistry's #1 most important resource that we will use. And everything we need to know is on here, starting with #1, hydrogen, and all the way up to number 118. We've got lots of information on here. We're given the name of the element that's on top. We're given its atomic number, its symbol, its atomic weight, and we're going to get into how to read all of this very shortly. Let's get a little bit more into elements. The stories behind some of the names of the elements are actually pretty fascinating. Many elements have names and symbols with Latin or Greek origins. Examples include helium, from the Greek word helios, meaning the sun. Lead, whose symbol is Pb, comes from the Latin word for heavy, or plumbum. More recently discovered elements have been named for their place of discovery or place of significance. Americium, Am, Californium, Cf, scandium, europium, francium, polonium. Those are just some of the examples. A number of elements are named for their discoveries or famous scientists. Curium, Einsteinium, fermium, Mendelevium, nobelium, seaborgium. These elements are not as common that you will find that we use in this class. Let's get a little bit more into the nitty-gritty of atoms and molecules. Atoms are the smallest particle of an element that retain the characteristic chemical properties of that element. Some elements like neon and argon are found in nature as isolated atoms. Others are found as molecules. A molecule are particles consisting of more than one atom in which the atoms are held together by chemical bonds. For example, molecular elements that are colorless gases of the air, like nitrogen and oxygen, are found as diatomic molecules, N2 and O2. You can see up here in the top left corner, oxygen is never found just O. Oxygen is O2. As well as, let's say, deep purple iodine. Iodine is always found as diatomic. Orange liquid bromine is Br2. There are 7 elements that occur as being diatomic. And here's the 7 list down here. I also like to remember them as Brinkelhoff. Brinklhof. So anytime you see bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, they're all listed down here. Anytime you see them by themselves, they're always going to be diatomic. There's going to be 2 of them. Again, some elements are monatomic, like we can see helium up here in the top left, meaning that they're just a single atom in their molecular form. Other elements contain 2, the diatomic, or more atoms, and others contain even more. So a form of oxygen called ozone, it's O3. There's 3 oxygens altogether. These are still elements. We wouldn't call them a compound or a mixture. There's still one single element. They're either monatomic, diatomic, or in another case, sulfur has 8 atoms, S8. All elemental molecules are made of atoms of a single element. Sometimes it's hard to think about how elements relate to our everyday lives, but we all know how important our cell phones are to us. And it's pretty interesting to see that almost 1/3 of naturally occurring elements are used to make a cell phone. For instance, the case components contain polymers such as ABS and or metals like aluminum, iron, and magnesium. The processor components, we've got silicon, copper, tin, gold, yttrium. We've got the screen components, silicon oxide, strengthened by adding aluminum, sodium, and potassium. And of course we have our battery components, lithium combined with other metals like cobalt, iron, and copper. Pretty neat to think about all of that. Moving on to our next section on compounds, you're going to be able to use the term compound correctly and understand the law of definite proportions or the law of constant composition. We've got a lot of information on this page. Remember way back when we were talking about pure substances and mixtures? Well, pure substances we said were elements and compounds. So this is part 2 of what a pure substance can be. Compounds are held together by chemical bonds and referred to as a chemical compound. There's a fixed ratio of elements. For example, let's look over here where it says compounds. Water has 2 H's and 1 O. That is a fixed ratio. H2O, there are 2 H's and 1 O for water. Sodium chloride has 1 sodium and 1 chlorine in that compound. Ammonia has 1 nitrogen and 4 hydrogens. Even though there are only 118 known elements that we just said, there are over 100 million different compounds that have been identified. That is crazy. The properties of a compound, its color, its hardness, its melting point, all of those things are different from the elements that make it up. Compounds can be broken down by an ordinary chemical reaction. Examples of compounds are water, carbon monoxide, table salt or sodium chloride, sugar, caffeine, nylon, and rust. Here's some everyday examples of compounds. The sodium chloride, sodium bicarbonate, which is baking soda, Epsom salt, which is magnesium sulfate, sodium hypochlorite, which is bleach, sodium hydroxide, which is used as a drain cleaner. Here's another well-known example showing that chemical compounds are composed of 2 or more atoms. When I have solid sodium, so Na plus chlorine gas, and chlorine, remember, is a diatomic molecule, so Cl2, and we can see the reaction that it creates, and it makes sodium chloride, which is solid NaCl, and we can see the structure of Na and Cl, and then Na and Cl, and it makes a solid structure. A mixture of elements versus a compound. It's important to distinguish between a mixture of elements and a chemical compound of 2 or more elements. Pure metallic iron down here and yellow powdered sulfur right here can be mixed in varying proportions. In the compound of iron pyrite, however, there is no variation in composition. Not only does iron pyrite exhibit properties unique to itself and different from either iron or sulfur, it has a definite percentage composition by mass. 46.55% of this compound here is composed of iron, and 53.45% is composed of sulfur. And here's structure of what pyrite would look like. This would be FeS2. We can see up here, these drawings, we can see our element. I've got argon. So I've got atoms of argon existing on their own. It's not diatomic. We have elements of oxygen atoms. And remember, oxygen by themselves are diatomic. So even though there are 2 oxygens together, it is still an element. Element. Then I have a compound because I have 2 or more different types of atoms together. I have a carbon and 2 oxygens, so this would be CO2. Carbon and oxygen atoms joined to make carbon dioxide. And here's an example of a mixture. Notice I have element, I have N2s, 2 N2s, an O2, and argon. So I've got 3 different elements combined and a compound. Looking at chemical formulas, for example, we just got done talking about CO2. And we said that for every 2 oxygens, there was 1 carbon. Or H2O. For every 2 hydrogens, there's 1 oxygen. We have what's called the law of definite proportions, or the law of constant composition. And a compound has a definite composition by mass of its combined elements. That is a basic principle of chemistry. And we can look at a chemical formula, and it is an expression of the number of atoms of each element in a compound. So if we were to look at sulfuric acid right here, we can see here that we have 2 atoms of hydrogen combined with 1 atom of sulfur and 4 atoms of hydrogen. We can see here that we have atoms of an element. So we just have, oh, this says oxygen, but that wouldn't be correct. There would be 2 oxygens on each of these because oxygen doesn't exist as just O, right? It would look like this. This is nitrogen. Nitrogen's always N2. Oxygen should always be O2. Carbon dioxide, like we said, there's 2 O's. So each of these reds, 2 O's for every 1 carbon. And we can see here that we have a mixture of elements and compounds in air. The formula for water, like we just said, the H for hydrogen, it's followed by that subscript 2. So this subscript tells me that I have 2 hydrogens. Don't get confused and think that it goes with the O. If there's no subscript after the O, that tells me that I just have a single oxygen. In this case, methane, CH4. This tells me that I have 1 carbon and 4 hydrogens. In this ammonia, NH3, I have 1 nitrogen and 3 hydrogens. And we've already looked at carbon dioxide, 1 carbon and 2 oxygens. Water is 1 oxygen and 2 H's coming off of it. Let's look at a problem. Identify whether each of the following is an element or a compound. Bromine and hydrogen peroxide. Why don't you pause the video and try. How did you do? Here's another. Identify whether white phosphorus and carbon monoxide are elements or compounds. Check your answer. Let's interpret some chemical formulas. Parentheses may be used to clarify atomic composition. Ethylene glycol, a component of some antifreezes, has a chemical formula of C2H4OH2. Now what this means is that these parentheses tell me that I'm going to have 2 of what is in parentheses. So ethylene glycol would consist of 2 carbons, 4 H's, and then 2 OH's. So I would have an OH and an OH. So 2 more O's and 2 more H's. So instead of 4 H's, that would be 6 H's. Let's try writing a chemical formula for vitamin B6, which is composed of 8 carbon atoms, 11 hydrogen atoms, 1 nitrogen, and 3 oxygens. C8, H11, NO3. Why don't you pause and try to figure out how many total atoms are in a molecule of glycerin? C3H5OH3 and nitroglycerin with this chemical compound. Did you get 3 carbons, 5 H's plus 3 H's, so 8 H's, and 3 O's. Remember, this 3 distributes to both of the things in parentheses. Let's look at nitroglycerin. Did you get 3 carbons, 5 H's? For O's, I had 3 O's here, and I had 3 NO2's. So NO2, NO2, and a third NO2. So 2, 4, 6 O's here plus 3. So that'd be a total of 9 O's. And that 3 distributed in here, again, we would have 3 N's. Let's try writing a molecule of B3 that has 6 carbons, 6 hydrogens, 2 nitrogens, and 1 oxygen. What is that chemical formula? Did you get this? Let's do some joining questions. Which physical state of water has the highest kinetic energy? Pause the video to see what you can get. Did you get steam at 115 degrees Celsius? How about this? Which of the following might best describe the particulate nature of a gas, such as helium? Hopefully you got number 2. How about number 3? Why is it more practical to store propane as a liquid rather than as a gas? Hopefully you got that the molecules in liquid propane are closer together than in the gas phase, so we can store more propane per unit volume as a liquid. Mineral water is what? A homogeneous mixture. Our next section is about physical properties. So we are going to be able to identify several physical properties of common substances, relate density to the volume and mass of a substance, and understand the difference between extensive and intensive properties and give some examples. Let's look at some physical properties of matter right here. Physical property is a characteristic that can be determined without changing the chemical identity of a substance. Some physical properties are the length of something, the color of it, its density, its mass, elasticity, pressure, volume, and luster. Again, physical properties can be observed without altering the composition of the substance. No new substances are formed, no substances are destroyed. Physical properties are usually reversible. They can be evaluated without changing the chemical identity, and you do not need to chemically change an object to see them. Think about it. You can recognize your friends by their physical appearance, their height and weight, and the color of their eyes and hair. The same is true of chemical substances. You can tell the difference between an ice cube and a cube of lead of the same size, not only because of their appearance, one is clear and colorless and the other is a lustrous metal, but also because one is more dense than the other. Obviously, the lead is more dense than the ice. Properties like these, which can be observed and measured without changing the composition of a substance, are called physical properties. The chemical elements that we're going to see, for example, clearly differ in terms of their color, appearance, and state, whether it's a solid, liquid, or gas. Physical properties allow us to classify and identify substances. And in this next table, we're going to look at a few physical properties of matter that chemists commonly use. We can look at color, like we said before. Its state of matter, is it a solid, liquid, or gas? Its melting point and boiling point. At what temperature does the solid melt? At what temperature does it boil? A physical property of water is that it melts at 0 degrees Celsius and it boils at 100 degrees Celsius. And the same could be true. We could look up the melting point of lead and the boiling point of lead. That would be a physical property. The density of an object is a physical property. The density of water versus the density of lead will be different. And that's something that we can use to identify those substances. The solubility, electrical conductivity, malleability, ductility, viscosity are all physical properties. Speaking of density, what is density? Density is the ratio of the mass of an object to its volume, and it's useful for helping us identify substances. Here is this equation that we can use. Density is equal to mass divided by volume. Sometimes I like to show my students and put it into this form. If I can say that density, D, is equal to mass over volume. So you cover up what you want to find. If I wanted to find density, I would cover this up and say D is equal to M over, or divided by, V. Now if I were to switch this up, and let's say I wanted to find the mass of an object. So if I wanted to find the mass, I'm going to cover up mass. Mass is equal to density times this line right here, since they're next to each other. Density times volume would give me the mass. And if I wanted to find the volume of a substance, I would simply cover up volume and say that the volume is equal to M divided by D. So mass would be M over D, or mass divided by density. Now let's think about what density really means. Let's look at this picture right here. Density and states of matter. Let's say that I have a certain volume, and notice that my solid particles are very tightly arranged here. If I were to think of each particle having the mass of 1, so I have more particles in a given volume. This is more dense than this, or my liquid. So as a liquid or a solid, notice that there are fewer particles in the given volume. So it would be like me saying, let's say I had 30 divided by 10. Let's say my volume of each of these is 10 cm3. Let's say that my mass, let's say there was 30 little atoms in there. Let's say that there's 8 atoms in there. So 8 divided by 10. And let's say in this we've got 1, 2, 3, 4. 4 divided by 10. Obviously this guy, 30 divided by 10, is going to be larger than 8/10, which is even larger than 4/10. So the density is showing us the certain amount of mass per volume. We can see, looking at these two, the one that is more dense is the one that has more mass in a certain volume. You could easily tell the difference between an ice cube and a cube of lead that's an identical size. Lead has a density of 11.35 grams per cubic centimeter. Ice has a density of 0.9, so the density of lead is greater than the density of ice. Now, physical properties can be affected by temperature. Let's look at the density of water when temperature changes. So if I have the density of ice and liquid water, both is 0 degrees, look at how it changes. The density of water is greater for liquid water than it is for ice. And notice when my density of water gets to 100, my density of water gets smaller, 0.95836 as opposed to 0.99984. That is a physical property that can be affected by temperature. Let's look at a problem. Let's say that we have an automobile battery that contains 2,346 grams of acid. This is a unit of mass. If the density of the battery acid is 1.84 grams per milliliter, so we know that's our density, what volume, so I'm going to say volume is a question mark. What volume of acid is in that automobile battery? Let's write down that little equation here where I said density is mass over volume. We want to find volume. So my equation would be volume is equal to mass divided by density. Let's plug in what we know. We know that our mass is 2,346 grams and that we were told our density is 1.84 grams per milliliter. Why don't you pause this and get your calculator out and let's see what we get. Did you get 1,275 milliliters? Hopefully you saw that grams and grams would cancel out, leaving us with just milliliters. Let's try another problem here. We have a piece of rope used for water skiing. It floats on water. But another polymer from soda pop bottles sinks in water. Put the polypropylene, the tetraethyl polymer, and water in order of increasing density. Pause the video and put them in order. Because my polypropylene rope floats in water, that's going to be my least dense, and it wants increasing density. So this polypropylene is going to be the first one because it is least dense. Then we would say water, and then we would say our soda pop bottle because it is sinking. Here's another example. See if you can figure out which liquid has the greater density. Hopefully you saw the vinegar is more dense than the olive oil. Moving on to our next topic, we are going to look at extensive versus intensive properties. Extensive properties depend upon the amount of substance present. The mass and volume of samples or the amount of energy transferred as heat are examples of this. Then we also have intensive properties, and intensive properties do not depend on the amount of a substance. For example, a sample of ice will melt at 0 degrees Celsius, no matter whether you have an ice cube or an iceberg. Density is another example. The density of water is always 1. I could have a small cup of water, or I could have a large body of water like Lake Michigan. The density of water is 1. Here's a little guide down here to show us that intensive properties do not depend on the amount. If you are an introvert, you don't care what people think. You are doing your own thing. So think about how intensive does not depend on how much you have. The temperature, the boiling point, the concentration. If I made a large batch of lemonade and I poured a small glass of that lemonade versus a large glass of that lemonade, the concentration is going to be the same. It doesn't matter how much I have. Versus extensive properties depends on how much you have. If I had a small glass of lemonade and I weighed it versus a large glass of lemonade and I weighed it, the weight would obviously be different. So that is an extensive property. The length of something, the volume of something. Again, if I had a small glass of lemonade versus a large glass of lemonade, the small glass is going to have a smaller volume, the large glass is going to have a larger volume. Take a second to read through this problem and figure out which of these properties are extensive properties and which are intensive properties. And then check your answers. How did you do? Here's another one. Take a second to identify whether each of the following properties is extensive or intensive. How did you do? Moving on to section 7, physical and chemical changes. You're going to be able to explain the difference between chemical and physical changes and identify several chemical properties of common substances. Changes in physical properties are called physical changes. In a physical change, the identity of a substance is preserved, even though it may have changed its physical state or the gross size and shape of its pieces. For example, here I have solid ice, but it can melt, so it does require energy, but it will then become liquid water. It is still H2O as solid ice, and as liquid water, it's still H2O. And that liquid water can then freeze, it can release energy, and it can become solid ice. A physical change does not result in a new chemical substance being produced. The particles present before and after are the same. Again, just like this example, I still have H2O. An example of a physical change is the melting of a solid or the evaporation of a liquid. In either case, the same molecules are present. Their chemical identities have not changed. Here's some other examples. Let's look at letter A. We have solid butter that is being heated and it's making liquid, melted butter. For letter B, steam is condensing inside of a pot. It's a physical change. Water vapor is being changed into liquid water. You can heat alcohol into vapor. It's still C2H5OH. Like I said in the previous slide, we can freeze water. We can recycle aluminum cans into aluminum foil. It's still aluminum. We can cut hair. Even though it might be shorter, that's okay. It's still hair. Some other physical changes, we can chop wood. We can shred paper. We can mix gray marbles with green marbles. Now, a physical property of hydrogen gas is that it has a low density. So let's say we fill a balloon with it, it's going to float in the air. Now let's say I take a candle and I bring it up to this balloon. The heat causes the skin of the balloon to pop, and the hydrogen gas mixes with the oxygen gas in the air, and the heat of the burning candle sets off a chemical reaction that produces water. This is an example of a chemical change when one or more substances, which are termed the reactants, are transformed into one or more different substances, which are called products. The representation of the change using chemical formulas is called a chemical equation. So notice here, I have hydrogen, H2. Remember, we already talked about hydrogen is never just H by itself. It's a diatomic molecule. It is in Brinkelhoff. So we have our hydrogen, and it's reacting with, so we would represent that as a plus. Oxygen, O is also never by itself. It's always diatomic. So we have two elements reacting. These are our reactants to produce products of water, H2O. Notice that our products are completely different from my reactants. So some chemical properties always involve a chemical change. Chemical properties explains how one substance acts in the presence of another. New substances are formed, old substances are destroyed. It's usually irreversible. When a chemical change occurs, the composition of a substance changes because another substance is formed. Some clues, this is a big one to write down, some clues that a chemical change happened is that there is a permanent color change, that there is a temperature change, that there is an odor produced or bubbles produced. That means that gas is being produced or as a product, or if light or heat from the release of energy is being produced. Here's some other examples of chemical properties that you can look at. Here's some more examples of chemical changes. Notice in letter A here, we can see that copper and nitric acid, so those would be the reactants, undergo a chemical change to form copper nitrate and a brown gaseous nitrogen dioxide. Let's look at B. During the combustion of a match, cellulose in the match and oxygen from the air undergo a chemical change to form carbon dioxide and water vapor. Letter C. Yum. I know the picture isn't exactly appetizing at the moment, but cooking red meat causes a number of chemical changes, including the oxidation of iron in the myoglobin that results in the familiar red to brown color change. I prefer mine medium rare, personally. Letter D, we have a banana turning brown. It's a chemical change. A new, darker, and this says less tasty substances form. Now, I think this would form tasty banana bread, in my opinion. Another chemical change. We have sodium metal, so Na, right here, Na, reacting with chlorine gas. So here's my sodium, here's my chlorine gas. Chlorine, again, remember, is a diatomic. Cl2, it's in Brinkelhoff. And here's my Na. So I have elements of sodium and chlorine reacting to form sodium chloride or salt sodium chloride. And notice this beautiful matrix that it forms. One Na with one Cl, one Na with one Cl. So here's kind of a little breakdown just showing differences between physical changes and chemical changes. Let's do some practice problems. How about you read these, pause them, and then I will pop up the answers. Next question, why don't you pause to read so then you can figure out which answer is the correct answer. Take a minute to classify each of the following changes as physical or chemical. So this one you're looking at all of them and classifying them all. Hopefully you got those answers. Check these ones out. Classify each of the following. See how you did? Now we're moving on to section 8, looking at energy. We're going to identify types of potential and kinetic energy and recognize and apply the law of conservation of energy. A crucial part of many chemical and physical changes is defined as the capacity to do work. You do work against the force of gravity when you carry yourself just by walking or carrying hiking equipment up a mountain. That's pretty extreme. The energy to do this is provided by the food you have eaten. Food is the source of chemical energy, energy that's stored in chemical compounds and released when the compounds undergo the chemical reactions of metabolism in your body. We look at nutrition labels and we can see how many calories something has. That's the English unit. Chemistry, we will use the metric unit. So we will look at joules. Energy is a unit of joules in our chemistry class. Chemical reactions almost always either release or absorb energy. Let's look at the law of conservation of energy. Energy is converted, not created or destroyed. So let's say we have this person standing on a diving board. You have considerable potential energy because of your position above the water. But then you dive off of the board. Once you dive off of the board, some of that potential energy is converted into kinetic energy. During the dive, the force of gravity accelerates your body so that it moves faster and faster. Your kinetic energy increases and your potential energy decreases. And the moment that you hit the water, your velocity is abruptly reduced. And much of your kinetic energy is transferred to the water as your body moves the water aside. Eventually you float to the surface and the water becomes still again. If you could see them, however, you would find that the water molecules are moving a little faster in the vicinity of your entry into the water. That is, the kinetic energy of the water molecules is slightly higher. Potential energy and kinetic energy can be interconverted. For example, let's say water falls over a waterfall. Its potential energy is converted into kinetic energy. Similarly, kinetic energy can be converted into potential energy. The kinetic energy of the falling water, it could turn a turbine and produce electricity, which can then be used to convert water into hydrogen gas and oxygen gas by electrolysis. Hydrogen gas contains stored chemical potential energy because it can be burned to produce heat and light or energy. And this is the last slide for this section, looking at the energy basics. 2 types of main energy. Kinetic energy, looking at the energy that's associated with motion, and potential energy that results from the object's position. So take a minute and go through to see all of the different types of kinetic and potential energy.